Hello everyone, today in this video we'll be discussing the module 5 of my microcontroller, and in this module we mainly have about the caches. Okay, you know what is a cache, right? Cache means if we are doing some operation in the phone, like some program is running and we want to fetch some data, and the data, instead of fetching from the main memory, we'll be having a cache in between so that we can easily access it from here only. And cache stores what is recently accessed. Okay, means if you're accessing some data very frequently, like your name, suppose that name will be stored in cache rather than in the main memory. Okay, main memory also it will be there, but in cache also it will be there, so that the accessing will be easier. The most frequently used data will be stored in a cache. So we'll be discussing about that, how it is working in the microcontrollers perspective, and what are the different policies present. So make sure you watch this video till the end, so that you can easily score more than 80% marks in the exam. And please do like and subscribe, it helps me make more videos like this. And without wasting more time, let's get started. If you have any question, you can DM me on Instagram. So the first topic is memory hierarchy and cache memory. Okay, so what is a cache? Definition of a cache: a cache is a small fast array of memory placed between the processor core and the main memory. Okay, processor core is your phone and the main memory is the main memory. In between that, cache is stored. Okay, and it stores portions of recently referenced main memory. Okay, recently referred to the main memory, what data it is there, that will be stored in the cache. The issue is that cache fills quickly and needs to be replaced with the most important data. Now suppose you're accessing a lot of data and cache does not have that much data. Okay, cache will be smaller size, which will be storing only the most important and recently accessed data. So if you are accessing more data, it should replace the existing ones to put the new data. Right now, which one should be replaced? For that, some policies are there and algorithms are there, strategies, we'll be discussing that. Okay, so before that, this is the memory hierarchy, like how memory is there. Okay, so the largest data which you store, that will be for longer time also, like it is a permanent data. Okay, so that will be in the bottommost layer, which is called as secondary storage. It will be stored in a disk, tape and network storage. Okay, this will be having large data and this will be not accessed much. Okay, now coming up, we have the main memory, in which the daily data which we require, that will be stored. Okay, it can be stored in the flash or other board level non-volatile memory. Non-volatile means when we close the system, it should not go off. Okay, volatile means it will be deleted after we close the system. Non-volatile means it will not be deleted. So that is in the main memory, and we will be having two types of main memories: DRAM and SRAM. SRAM is the static RAM and DRAM is the dynamic RAM. Okay, so the configuration difference will be there, and one of them will be more better than the other one. Okay, SRAM will be more faster than the DRAM. Okay, after that comes the chip, which is the cache. Okay, inside the cache will be having the most accessed data, which is present in the tightly coupled memory. Processor core, it will be having the register files, level 1 cache, and write buffer is also used in there. Okay, to access the data from the main memory. So this is how the memory structure is. As you go up, the size of the memory decreases, but the speed will increase. Okay, it is like that. The memory will decrease, but the speed will increase. Okay, as we go up. Okay, so this is the memory hierarchy diagram, very important question from exam point of view. Next, the cache relationship with the main memory involves transfer of small blocks of data between the slower main memory and the faster cache memory. Okay, now in this diagram you can see there is no cache present. In the top diagram we have a processor and we have main memory. The processor and the main memory, the access is happening to write and read the data, but it is very long distance and it will be very slow. To avoid this, what we do is we'll be introducing a cache in between, and we'll be introducing a write buffer. So basically what will happen, the most access data will be present in cache. How it will be present in cache? Initially it will be empty. Next, when we access some data, that all data will be written in cache. Okay, first it will be fetched from the main memory and it will be slow only, but for the next time it will be faster. Okay, it will not again go to the main memory, it will be accessing from the cache itself. First time it will be gone to the main memory, it will be written in the cache and it will be accessed fastly from here afterwards. Okay, and if you want to write some data, again you will not be using this method. To write the data, first it will be written in the cache, and after it's written in the cache, the next process will happen, means it will continue the process, it will not wait for writing to the main memory. So it will be written to the cache and cache will empty it to the write buffer. Okay, so whatever is written here, which is to be written in the main memory, it will empty it to here, so the cache is also empty, it can access the more data more frequently. Okay, and write buffer will later on slowly do it, it will not halt the processes going on here. Okay, that's why the cache and write buffer is used. Got the point? Okay, next is caches and the main memory management unit. Okay, cache can be located at two places. Okay, the cache which I am talking about, between your phone and the main memory, it can be located at two places. Which are those two places? The first one is between core and MMU, okay, and another one is between MMU and physical memory, okay. So there are two types here. As you can see, there is MMU here, which is memory management unit. Between the phone, which is the processor, and the main memory, there is cache. Cache can either be before the MMU or after the MMU. So what difference does it make? If it is before the MMU, MMU means what? Memory management unit. It manages all the addresses and the data and so on, those things, okay. So between the main memory and the memory management and the processor, if the cache is stored here, you can get the data more fastly if, with respect to the processor. But if it is stored between the MMU and the main memory, if the writing task is more, you can easily write that more tasks here, okay, but fetching will be harder. So mainly this one will be used because we'll be not writing much, we'll be fetching the data more. So cache is used in before the MMU. And when we use cache before the MMU, it is called as logical cache. If it is used after the MMU, it is called as physical cache, okay. Next is principle of locality of reference explains the performance improvement provided by the addition of cache memory to our system. Now, principle of locality of reference means what? Where which all data which is present here that is most frequently accessed, that it will calculate and keep. Means it will give us information of this data is more access, this data is more access, this data is more access. Once we have this information, we can place cache such that it will access those kind of data very frequently. Okay, so that is called as principle of locality of reference. The next topic is the cache architecture. Okay, like we know about the cache. What is a cache? It will save us time fetching the data from the main memory. Instead of that, it will store here only. But how it is actually built? Okay, there are architectures for that. There are two architectures for that. One is the von Neumann and second is the Harvard architecture. We will be using von Neumann. Okay, most of the systems use von Neumann, but we need to know about the Harvard architecture as well. So in von Neumann, there is a single cache for instruction and data. As you know, the data is present here, and what is to be done with data, that will be written in where? Instructions. Okay, instructions will instruct us what to do with this data. Both this instruction and data form a crucial part of the system, and both of these will be stored together in one human architecture. But in Harvard architecture, both will be separate. Means data will be here and one cache will be associated with that, and instructions will be here, one cache will be associated with that. Okay, and connection will be there in between, but those will be separated. So that is called as Harvard architecture, in which it will be separate. We will be discussing about the one Neumann architecture. As you can see, this diagram is the von Neumann architecture. Okay, what you can observe from here is that three things are here. Address issued by the processor core. Here the address will be in the form of tag, set index, and data index. We'll be discussing what it is. Okay, before that I need to let you know that there is memory here, cache memory. Okay, cache memory looks like this. All the recently accessed data is stored here. Okay, all the recently accessed data is stored here, and cache controller will control what data to fetch and what data to write. Okay, instruction will come from here. It will compare. If it is present here, it will be taking it from here only. That will be called as a hit. If it is not present in the cache, it has to take from the main memory. Then it will go to the main memory, which is called as miss. Okay, and now in the cache memory you have lines. Okay, each line is called as a cache line. Okay, there will be many lines like that, and each of these will be having an address. Okay, that address will be associated with each of these to identify where it is present. Okay, now inside this, the data, you can see three things: directory store, status, and the data. Data is the actual thing which is stored in as in the form of words. Whatever is the data, our data which is stored in the cache. Status means is it valid or dirty. Valid or dirty means what? Valid means this bit is present inside this and it is a valid one, means it is a useful data. Dirty means it is modified and it is not useful, the data is changed. Okay, like that. That is a valid and dirty. By using valid and dirty, we can identify if it was the original data or some data we have made changes to it. Okay, and the cache tag will be there. Tag, you know, right? Something named like apple tag or banana tag. So like that, if you want to identify a cache line, you'll be identifying with a particular tag, and the tag will be given here. So suppose that I want to access this line, which is this line, third line in the cache. Okay, how will I access? I have to provide three things. First is the tag. That third line, what is the tag? Suppose it is orange, so I'll be writing here orange. Okay, then next I have to identify which cache page it is. Okay, this is the page. Like that, many pages will be there. This page address will be put in the set index. Okay, there will be many pages like this. As you can see, this is one page. Okay, like that, there will be many pages, and I have to choose which page I am talking about. So that will be there. And what data I am talking about, if I got the tag and the set index, I've got these two, I've selected this line, but line is not important for me. What is important is which data you're talking about. Is it word 1, word 2, word 3, or word 4, like that. Okay, so that will be specified here. So based on these three combinations, I'll be able to select a particular word from the whole memory. Okay, so this is how the cache memory looks like. Okay, and this is the von Neumann architecture. As you can see, the instructions as well as the data is present in the same location. Okay, and that's the same thing I discussed: directly store data section and status information. Three things: data, directly store status, and data information that is present here. Okay, now how does cache work? Okay, the basic operation of a cache controller. Cache is controlled by a cache controller. It is a hardware that copies code or data from the main memory to the cache memory automatically. Okay, so what does controller do? Controller's task is to fetch from the main memory what the data is required and find the data whenever it is required in the particular page. Okay, so that is the operation of a cache controller. It processes a request by dividing the address of the request into three fields I discussed: tag field, which is used to identify if it is banana, apple, or which tag it is. Okay, the tag is used to find out the particular line, and set index field will be used to find out which page it is. Okay, and data index field will determine which data you want to know. In the above figure, set index field determines the cache line. Okay, so here in this case, the set index, as you can see, this determines the whole set of cache lines. Okay, there will be 256 cache lines and that will form one page, and the set index will select that particular page will be having 256 lines, and tag will identify which line you are talking about. Okay, after the comparison. Now, if it finds the required data, it is called as cache hit. If it is not finding it in the cache, it is called as cache miss. If the cache miss happens, it has to go and fetch from the main memory. Okay. Now, the relationship between cache and main memory, how both are related. Okay. So this is the main memory, as you can see. This is the places where we store the data. Okay. Like that, many data is stored, and the addresses are also given here. Okay. Addresses for each data. All this data will be put in the one line. Okay. Means one line will be having one particular data, second data will be in the second line, third line, fourth line, like that. All the lines which are there, that will be present in this particular cache. Okay, and that will be identified by using the cache tag, valid or dirty bit, and the word which I require. Okay, so word will be stored in the data index, set index will be calculating how many lines are there till the end, and tag will be calculating which tag it is, so that to particularly map to that particular line. Okay, if I want grape data, okay, so I'll be putting a grape here, so that it will be selecting the cache line with the tag grape. Okay, so this is how the cache is connected with the main memory. Okay, that's also very important question. In a direct map cache, there are two types of caches. First is direct map, second is set associative. Okay, I'll discuss both. First, in direct map cache, each address location in the main memory is mapped to a single location in the cache memory. So as you can see, every location in the main memory, these are different locations, data will be stored in between. Okay, so each of these is mapped to one particular line. Okay, each of these has a separate line. This kind of mapping is called as direct mapping. Okay, direct map data. Next is set associative. Okay, I'll discuss this set associative in some time. Let's understand more about the direct map. The set index selects one location in the cache where all the values in the memory ending with the address 0x824 is stored. Okay, it is ending with 0x824 means this particular page which is there, this whole cache last word is 0x284. That means the whole set of related content will be taken, means one page it will map to. Okay, next is data index selects the word, half word, or byte in the cache line. In this case, the second word in the cache line. I want which word? I want this particular word. Where I will specify I want this word, I will specify it in the data index. Okay, next is tag field. It is a portion of the address that is compared to the cache tag value found in the directory dictionary store. So this cache tag will be available here to identify which line you want to point to. Okay, so in this example, 1 million possible locations in the main memory for every one location in the cache. Only one of the possible 1 million values in the main memory can exist in the cache memory at a given time. Okay, so out of 1 million, only one possible value can be existing in the cache. Okay, so cache is a very limited amount of memory. All the main memory, if it is stored in cache, what is the difference between cache and main memory? It will be same, right? Instead of that, what you do? You take the main memory, put it here in the place of cache. So what is the difference? There is nothing different there. So only cache will be having very less data. It will be just having 1 by 1 million data of the main memory. Okay, and that will be the most frequently accessed data. Okay, and that will be changing with time. If some data gets more access with respect to time, that will be stored in the cache and the previous data will be removed. That process of removing an existing cache line is a part of servicing a miss, is called as eviction. Direct map cache are subject to high level of thrashing. What is thrashing? Thrashing means, suppose that there is one candy. Okay, you and your friend wants that candy. You and your friend are fighting for that candy. That is called as thrashing. Fighting for the same location in the cache memory. Two data is there. Two are also both frequently access data. They want the place in the cache memory. Okay, so that is called as a thrashing. Okay. Now, an example of thrashing is given here. There are two functions, routine A and routine B. Now, routine A and routine B both want to come and sit in 0x480. Why? Is 0x480 a golden seat? No, it's not a golden seat. It is what? It is the ending address. Okay. So, algorithms will be there which will be deciding which location you should be selecting. Okay, so in this case the ending address is the one which is deciding where it is to be stored. So it will be stored in 480. Okay, 480 is present here at the last three digits, so 0x480 it is trying to access. Okay, so it will be doing it routinely, like this is a while loop, right? So what will happen? Routine B will sit, then routine A will come, push routine B, then routine B will come, push routine A, and routine A will sit again. There will be a lot of thrashing if you use the direct mapped method. Okay, because every main memory line is accessing one particular cache memory here, so that there will be thrashing there. Okay, so to avoid thrashing, or in the other sense avoiding is not totally possible, it will be we are just we have the techniques to reduce the thrashing as of now. Okay, we cannot totally avoid thrashing, we don't have such algorithms. Now to reduce the thrashing, we'll be using set associativity. Okay, this technique is designed to reduce thrashing. So what magic does it do such that the thrashing will reduce? Okay, let's discuss that magic. So in set associativity, the structure is changed. Okay, in map main memory, I mean the direct map, what is the structure? Direct structure. It is just a main memory and a cache. But here what will happen? This structural design feature is a change that divides the cache memory into smaller equal units called ways. Ways is a new concept introduced here. What it means is it will divide the whole page into different multiple pages. Okay, now suppose that one page used to contain 256 line. Okay, like previously this contained 256 line 1, line 2, line 3 till line 256. But now what will happen is it will divide into 4 pages with 64 lines. Okay, so this will have 64 lines, this will have 64, this will have 64, this will have 64. What is 64 into 4? 64 into 4 is 256. So again the memory is same, but it has divided into different pages. Why? Because every time if it is the same value, like 480 is there, 480 get used to store here only. If another 480 comes, it will again point to the same location, but now it will be pointing to the same location in a different page. Like that, 4 times 480 will come, it will still get the space to be sitting. Okay, and it is observed that this algorithm will be giving us better performance. Okay, so that's why set associativity is used. Okay, now it can be increased. Now only you can think like it is already better, how can we increase it more better? Okay, you can increase it more better. That is also possible using the content addressable memory. Okay, CAM means what? Content addressable memory. What it does is it uses a set of comparators, okay, to compare the input tag address with the cache tag stored in the each valid cache line. So what it does is it will compare whether that cache is a tag is existing. For example, the tag orange is existing in these pages or not. If it is not existing, it can assign it to some other page, right? It works in the opposite way as RAM works. Okay, RAM produces data when a given address value, and CAM produces an address if the data value exists in the main memory. So if the data already exists in the cache memory, why you want to store it again in a separate page? You can use the same one, so it will just produce an address of it, okay, where it is stored, so that access can be possible and you can use that data. Okay, so that is the content addressable memory to increase the performance of the set associativity. Okay, now we had discussed about the write buffer, right? This is the main memory, and between the main memory and the processor, you'll be having an MMU. In between MMU and the cache, you'll be having a write buffer. What does write buffer do? Cache will be storing the data, and that will be transferred to the write buffer, and write buffer will slowly keep writing until then cache will be performing some other operations. So write buffer is an assistant of cache. Okay, what it is? It is an assistant of cache. So write buffer is a very small, fast FIFO memory. FIFO means first in, first out. So it is just like a queue. What came first, that will be first written. Second will be written. Third, it will be written third, like that. Okay, that temporarily holds the data that the processor would normally write to the main memory. So instead of processor writing to the main memory, processor has other works also. So it will hire an assistant which will be given the data, and that assistant will be writing the data. So that assistant is nothing but write buffer. Without write buffer, data is written directly to main memory and it will cause slowness. And with write buffer, data is written to the FIFO, which is the write buffer, and then to the system. Okay, now data written to the write buffer is not available for reading until it has exited the write buffer to the main memory. So write buffer, you want to read the data, that is not possible. It will again slow the system, so that option is not given. So you can read the data after it is written to the main memory. Okay, Next is measuring the cache efficiency. Now we have discussed a lot about cache. Now how we will know which cache is better? To understand which cache is better, take an example. Suppose that you are fan of apple and chicken. Okay, you want to eat apple, you want to eat chicken. Someone else wants to eat fish and cucumber. Okay, now in the basket which you have brought, okay, your home is here. In the basket you have brought some items. Okay, now in that items, if you have more apple and more chicken, at that time you will be satisfied, right? Because you are getting whatever you want from the bag itself. You are not going again home and bringing. And the other person who wants fish and cucumber, if suppose fish is there but cucumber is not there, the other person will just get fish and that person will be 50% satisfied. Now you tell me which one is getting more satisfied, you or your friend? You will be getting more satisfied because you have 100% whatever you want, it is present in the basket. The same thing applies here. Whatever the system wants, the more it is present in the cache, it is better. I'll repeat, whatever the system wants, whatever the data it wants, if it is present more in the cache, that is more better. If it is not present in cache, again you have to go and bring it from the main memory. That will be a worse cache. Okay, so the cache and its algorithm, which will ensure that most probably what data is required, that data would be frequently present. That algorithm will be the better algorithm. So this is how we measure the cache efficiency. The more the times the data is requested and it was present in the cache, that is called as the better cache. Okay, so hit is used for getting the data from the cache whenever it is required, and if the data was not present in the cache, you have to bring it from the main memory. It is called as miss. So the more number of hits means more data I'm getting from the cache itself. More hit means more better data. More miss means more worse cache. Okay, so it is expressed in the form of percentage. What is hit rate? Hit rate means how many times I got it from the cache divided by how many times I had requested. If I got 10 times and I had requested 12 times, the percentage is very high, 10 by 12. If I requested 100 times but I got only one time, it is a worst cache, right? Because there is no point. 99 times I'm going and bringing from the main memory. So the data which has more hits is called as better cache. Okay, the last topic is the cache policy. Cache policy means what? Now we have discussed about the cache. Now but policies are also there. Why policies are there? That is because, see, cache cannot store unlimited data. Okay, it has a limit. So which data it is to be replaced when another data is required. To select which data, for that some rules are there. Rules are nothing but policy. So three policies determine the operation of a cache. First is write policy, second is replacement policy, and third is allocation policy. So write policy determines where data is stored during the processor write operations. Okay, where data should be stored. It is to be stored in the cache, or it is stored in the main memory, or it is stored in the write buffer, or where it is stored. Okay, so write policy, write through is there and write back is there. Okay, through two methods to write the data. In write through, what happens? Suppose processor gave an output. I gave the processor data 1 plus 1. It gave me the result 2. Now 2 I cannot see forever in the screen. If I go back, the 2 will be erased. I have to store somewhere 2. Where I will store? If that 2 is written in the cache and the main memory, okay, in the cache and the main memory, it is called as the write through, and it is slower because you are manually writing it into the main memory without using any other thing. But write back means what? Data is written to the cache but not in the main memory. Later it will write to the main memory. Okay, so the time will not be wasted writing to the main memory. When it will be written to the main memory? Whenever it is to be deleted from the cache. Suppose cache is filled, new data has come, and this data has to be removed. Before removing, write the data. So it will be much more better rather than every data what you are getting writing every time to the main memory. Whenever it is required, that time only you will write to the main memory. That is the write back method, and this is faster one. Okay, so that's the first policy, how you are writing the data. Second is cache replacement policy, which means selecting the line which is to be used next time to fill during a cache miss. This basically means which line you have to choose to replace. That's it. Okay, so on a cache miss means you do not find the data in the cache, you've gone to the main memory to find the data. It must select a cache line from the available set in the cache memory to store the new information from the main memory. Okay, so you need to find out the line which is available, or if it is not available, which line should be deleted and put it in its place the new data. That finding it is called as cache replacement policy, and that algorithm decides. Okay, we'll not go into the algorithm, that is out of the scope of the syllabus. So but there will be algorithms for that. Okay, so the cache line which is selected for replacement, like from among this, which line selected, this line is called as victim. Okay, and ARM cache cores support two replacement policies. Now the algorithms are there, right? Algorithms are pseudo random algorithm and round robin algorithm. Okay, and round robin is cyclic replacement of the next cache. Means what it will do? It is present here, right? So it will replace this line, then it will replace this line. leaving some spaces, then it will replace this line leaving some space, again it will come second, fifth and seventh, then third, fourth and sixth, like that it will keep replacing. That is a round robin. After some point of time it will keep replacing. Pseudo random means it selects the next cache line to replace, so it is an order like that, first this, then this, then this and so on. Okay, so that kind of replacement is pseudo random. The following program demonstrates the performance difference between the both. Okay, this is just for your reference. Okay, this will, like this question will not be asked in exam, so you just need to understand. Okay, this is the code wherein you will be enabling the round robin and enabling the random function. Both are enabled and time is also set here, so that we'll be able to calculate how much is the time, and we are passing the data, calling the functions from here, and after we call the functions we will be seeing the results. As you can see in the results, round robin time it took 0.51 and random also it took 0.51. That is when the data set is 64. Okay, as you know 64 is a even number. I mean the number in which a particular page will be filled full, because 64 line is there. If we take 65, it will be another page just for one line. Okay, so in the case where it is filled fully and another page is not there, in that case round robin will be the best. It will perform and random enable will also be the same. But when it is 65, means another page has come, round robin will be very high, which is 2.56 seconds, and random enable will be that much only, little more. Okay, 0.58. So based on the two scenarios, the pages you can select round robin or random one. Okay, so this is the performance difference between the two algorithms. Next is the allocation policy on cache miss. Okay, this is the third one. Three policies are there. First one was about the what was the first one about? The second one is about this one, replacement. But the first one was about what? Write policy, right? So write, you already understood how do we write the data, whether we store it in the main memory or in the cache. Next is replacement, round robin and pseudo random, and third one is allocation policy on a cache miss. Now there are two strategies that caches may use to allocate a cache line after the occurrence of the first cache miss. Suppose I wanted some data, it was not present in the cache, I selected the data from the main memory and I brought it here where I will write it, that data. To write the data we will be using two strategies, read allocate and read write allocate. Now it depends whether you want to read the data or you want to write the data, right? So if you want to read the data, go with the first one, and if you want to write the data or you want to do both operations, go with the second one. So in read allocate, on a cache miss policy, allocates a cache line only during the read from the main memory. Whenever a read is happening, you'll be allocating a space. Okay, that is called as a read allocate. Read write allocate will be allocating a cache line for either read or write memory. Okay, so any operation which is made to read or write which is not in the cache memory, a cache miss will be there. The data will be fetched from the main memory and it will be written or read, whatever it is required if you use the second strategy. Okay, so the to facilitate all of this we have some co-processors. Okay, co-processors 15 in caches. Okay, so there are 15 registers. What it does is it will be helping to do the above operations, controlling the cache and where it is to be written and where it is to be taken, which algorithm is to be used, which replacement policy is to be applied at this particular situation. All will be happened by a controller which is assisted by 15 registers. Okay, so we'll not discuss the 15 registers here, we'll be discussing the most commonly used. So first one is system control register. What it does, it enables and disables caches and MMU. If caches and MMU is not required, it will enable and disable it for better performance. Cache size ID register, it provides a cache line size, associativity and the number of sets, the information about it. Okay, and cache size selection register, what is the level and the type of the cache, means if it's a greater data we need bigger cache, right? That will be decided by this coprocessor. Next one is cache type register, which is the details of architecture, von Neumann or hardware architecture, which one you are using. Okay, auxiliary control architecture enables optional cache and performance features. It will give us the results of how better it has performed. Then the next one is cache maintenance registers. It will clean, invalidate, flush cache or TLBs, means it will keep maintaining and remove the unwanted data and keep only the relevant data. Like that it will be doing the operations. Okay, so the control system usually calls these routines as a part of its memory management activities. Memory has to be managed. To manage the memory, these are the slaves present. Okay, so they will be performing those things. Okay, and the control will be giving commands and these will be performing those particular routines they have been assigned. Okay, that's all for this video. If you found this video helpful, please like and subscribe. It helps make more videos like this, and thank you so much for watching. I'll see you in the next